All right, so it's 2 o'clock by my watch. So let's get started with the session then. So this is the third session on the series of testing general relativity given to us by Professor Pani. As usual, if you have any questions, please feel free to either raise your hand and I can allow you to unmute and you may ask your question orally. Alternatively, you may also type your question in the chat and I can read it out to Professor Pani. All right, Professor, over to you.
Thank you very much, and good afternoon. Welcome to this last lecture on testing general relativity. Today's lectures will be about a ring-down test, mostly. So yesterday we talked about in-spiral-based test using gravitational wave signals in the, say, pre-merger phase. And today we will focus on the merger and post-merger phase, discussing the ring down in modified theories of gravity and in modified black hole scenarios. Before going there, I would like, for completeness, to cover two other topics very briefly. One is gravitational wave propagation tests. And the reason is that everything I said yesterday was concerning the generation of gravitational waves, how generation of gravitational waves is different.
Sorry, Professor Pani, sorry to interrupt you, but suddenly the video has gone blurry. I don't know why. Yeah, yes. Now it's clear. Yeah.
Okay. Somehow this webcam is losing focus. Okay, but it should be fine now.
Yes.
Okay, yeah, so I was saying everything I said yesterday was about how gravitational waves are generated differently in different fields of gravity, or if the objects are not the standard black holes in general relativity. But there is also another possibility that besides different generation, also the propagation of gravitational waves might change in alternative theories of gravity. And in fact, we know that GR propagates only 2 degrees of freedom, traveling at the speed of light, and therefore is described by a dispersion relation of this form here, where k is the wave 3 vector, omega is the frequency, and this tells us that both the group and phase velocity of a gravitational wave is the speed of light. What gravitational wave propagation tests try to constrain are modification of this dispersion relation. For example, by including an extra term due to the mass of the graviton, mg, which will come with some power of the Planck constant h bar, or generic corrections, which are parameterized by some coefficient a, that modify the dispersion relation with some generic power of the absolute value of this vector, ki to the power of n. So GR is recovered when this guy is 0 and when the mass of the graviton is 0, but in general we might have corrections that, depending on the theory, might change the dispersion relation with different powers n of this dependence on the K momentum. In particular, theories that try to find a UV, so ultraviolet completion of general relativity, so modify gravity at higher energy. Some examples are Lorentz-Violeti theory of Java gravity. They have a dispersion relation which is modified precisely at large momentum, and some of them are described by a coefficient n equal to 2, which of course modifies this dispersion relation and also tell us that gravitational waves in this theory propagate at a speed that depends on the frequency. The good news is that gravitational wave propagation tests can be implemented on top of any gravitational wave generation test, in the sense that you can model in GR or in any modified theory of gravity. On the top of that, we can implement a dispersion relation of this form, which will modify the signal and allow us to constrain this effect. I should also mention that there are several parameterizations for gravitational wave propagation test. This one is pretty common and it allows us to put constraints on the mass of the graviton and this sort of dependence on the momentum. There is also another one used mostly for cosmological purposes that depend on the other factor H, and there are some free coefficients alpha n and alpha p. And this parameterization is used in what is called the context of parameterized post-Friedman test of gravity, which are related with a parameterization that deforms the standard Friedman cosmology and linear perturbations, adding extra coefficients that are, they acquire a specific value in general relativity. And these two parameterizations are not equivalent to each other, they are actually complementary. For example, this one can test a non-zero mass of the graviton, while this one has this term here that is actually imaginary, and tests the essentially dissipative part of the propagation of gravitational waves due to the expanding universe. So this is taking into account the expansion of the universe. So they are not equivalent, but there are different ways to test the formation of the standard gravitational wave propagation, either in a expanding universe or in a local universe. Okay, an important point to mention is that the most stringent test on the speed of gravitational waves actually come from sources that have an electromagnetic counterpart, and in fact a very strong constraint has been placed after the detection of the first gravitational wave signal from a binary neutron star coalescence, GW17 or 0817, because in that case the electromagnetic counterpart has been detected essentially in coincidence with the gravitational wave signal, and by this coincidence one is able to put a bound, a very simple one, on the speed of gravitational waves, in particular how much different the speed of gravitational wave can be compared to the speed of light of electromagnetic radiation, and the bound is impressive. The speed of gravitational waves, let me call it CGW, is different from 1 in 1 part in 10 to minus 15. So essentially, it's a great confirmation gravitational waves propagate at the speed of light. Okay, and of course, the same way one can constrain the PPE parameters I was mentioning yesterday, one can constrain this parameter here, this exponent here, or this post-Friedman parameters here in a Bayesian sense, just by modeling this signal, this effect into a proper signal and analyzing it. Okay, the other, before moving to the read-down, the other comment I want to make is related with gravitational wave polarization. These are also a different kind of test, sort of model independent test that one can perform. And the idea here is that GR, as I was saying, propagates only 2 degrees of freedom. But in fact, for a generic metric theory of gravity, there are in total 6 degrees of freedom. So 6 polarization that a gravitational wave can have, 2 scalar and 2 vector modes, which would add to the spin 2 polarization that exists in GR. And depending on the theories, these 6 degrees of freedom can be actually less. So this is the maximum value. But for example, massive gravity, so theories in which the gravitational waves propagate a massive spin 2 perturbation would have 5 degrees of freedom. Scalar tensor theories will have 3 degrees of freedom. certain modified theories of gravity still have 2 degrees of freedom, so it really depends on the theory. But these kind of tests are interesting because they can probe different theories in a model-independent way. And the idea here is that one needs an array of detectors, so a network of detectors, and project the signal across different directions identified by the detectors, and construct what are called the null strings, which allow to essentially find a basis for the different polarizations and then test the different polarizations in this way. It's interesting that if one has m modes in a theory, with m therefore equal or smaller than 6 in any given theory of gravity, and d detectors, in order to make the most general test, the number of detectors d must be bigger than n plus 1. There are particular situations in which this actually can be smaller, but in order to make sure that one has enough projection essentially to test all modes, at least one needs this inequality to be saturated. And of course, the more detectors we have, the better, because it allows us to construct different orthogonal projection and therefore make more tests. And if, for example, we want to test 2 polarizations, we will need 3 detectors in general. If we want to test 3 polarizations, at least, except for particular configurations. In the paper I was mentioning yesterday, the one on test of gravity with the third gravitational wave catalog, there is a very detailed analysis, actually the state-of-the-art analysis of this polarization test, doing a Bayesian inference, considering different hypotheses in the number and the nature of modes of the polarization. In the sense that we know, I mean, what we want to do is compute the base factor between the possibility that GR is, I mean, that gravitational waves are purely tensorial with 2 polarization, and T stands for tensorial, and then one can compute the base factor, for example, confronting this hypothesis with the one that gravitational waves are purely scalar, or that they are purely vector, or maybe they are scalar vector, maybe they are scalar tensor, and so on and so forth. And there is a very detailed analysis there. The results are interesting in the sense that there is very strong evidence the signal is in fact tensorial as compared to a purely scalar or purely vector signal, which is sort of expected. However, it's much more difficult, given our current signals and the number of detectors, to exclude the possibility through this test that the signal is a combination of tensorial plus scalar modes, for example. So the base factor for the hypothesis tensorial versus scalar tensorial is actually, I mean, does not give very strong evidence. And the same is true for vector tensorial or scalar vector tensorial. So these are tests that are potentially very interesting, especially when there will be in the future a larger array of detectors that will allow for more stringent tests. Okay, finally, before moving to the ring down, let me just mention something that came up in a question yesterday. So how to distinguish this effect from something else? So suppose that we detect an anomalous either gravitational polarization or gravitational wave generation parameter or propagation parameter. I mean, we will be sure that that is due to modified gravity, so beyond GR effect or something else. In fact, an important point that one should always take into account is to compare gravitational wave test. Sorry, I mean beyond GR effect versus what I would call environmental effect. And these are effects that modify the waveform due, for example, to matter configuration or matter fields around black holes. And these are typically very small effects, in fact, and this is why they are typically neglected in any standard search. Some anomalous effect should be detected, then it would be very important to test whether it might be competitive with environmental effects. Let me just give you an example. A gravitational pool so essentially just the presence of some matter configuration around the binary that produces a gravitational interaction is a minus, I wrote it down here, a minus 3 PM effect. So modifies the inspiral waveform that we discussed yesterday at minus 3 Pn order. So we have a term that goes like the gravitational wave phase, the Hamiltonian order. 1 plus some coefficient divided by v to the 6. So it's an effect again that is very important in the early spiral when the velocities are very small. And this coefficient alpha here, let me call it delta alpha to follow the notation we had yesterday. This coefficient delta alpha here will depend on the density of the matter configuration around the binary. This density, I mean, for T is so small, then even if this effect is very strong at small velocities, it would be totally negligible. But again, it's something to keep in mind at the moment you find possibly some anomalous effect. And similarly, for example, gravitational drag, so the so-called dynamical friction effect, will introduce a term that I think is minus 5.5 PM. So it's even more important at small velocities, and again, depends on the density, the local density of the binary. Of course, an important point would be that a modified gravity effect should, I mean, of course, it depends a bit on the theory and on the model under consideration, but some of them are universal in the sense that we should expect them in all sources or in most sources. For example, dipolar emission, given a theory, can be zero for example, binary neutron stars, but it should be non-zero for all binary given a theory. And therefore, if there is an anomalous effect which could be interpreted as dipolar emission in a single event, one should explain why that event shows a particular anomalous effect while others do not. While environmental effect might actually occur for a single source or for different classes of sources, because it really depends on the environment in which these sources live, and it might be different depending on the source. So is something that one has to keep in mind. I would say the moment something weird might be possible detected, otherwise they are very small. Okay. So I don't know if there are questions so far.
Actually, I do have a question, Professor Pani. So my question is regarding the propagation of these different polarization modes of gravitational waves. Are there theories where the two polarizations could travel at different speeds, or are all theories expected to predict that both polarizations should travel at the same speed?
I don't have any specific example, but yeah, if I understood properly the question, yes, there are cases in which at least some of the polarizations propagate at the same speed. Yes, it's not. For example, it is possible that if there are extra polarizations, say the vectorial ones propagate at a given speed, while the tensorial ones propagate at a different speed, but in the same, say, group of speeds of polarization, they do propagate at the same speed. So that is really model dependent and depends on the theory. Overall, a generic effect is probably that the group and phase velocity is generically different, except for particular theories which sort of enforce this. And that is something else that can be used. And in fact, there is an effect in the waveform due to this. After one implements these different dispersion relation in the signal, and it's something that one can look for.
I see. Thank you.
Okay, so let me move now to the main topic of today's lecture, which are ring-down tests. As I was mentioning yesterday, in a coalescence, of course, you well know, the initial part phase is the spiral, then we have the merger of the volume, which is highly dynamical and not it cannot be described within perturbation theory or within post-Newtonian theory. But after the merger, the final object, the remnant, settles down to a stationary configuration, emitting gravitational waves, and this emission, at least after a certain time after the merger, is an important point I will come back later, can be described within perturbation theory. So essentially, by considering small perturbations on the top of a stationary black hole, and this is why the perturbation theory is so important to discuss the ring down. And the signal in general relativity is modeled as a superposition of damped sinusoids, and I'm sure that during the lectures by Eric Poisson, you have learned much about it. So I will just give a very quick overview in a simplified case, just to put everyone on the same page, and then move on to discuss the test of ring down and quasi-normal modes. So let me take a simple example. I will take a metric. So let me focus on spherical symmetry, and then later on we'll discuss what spin does the ring down. So for spherical symmetry, we can take a generic spherical symmetric line element of this form. From here. So f and b are two generic radial functions. Of course, for a Schwarzschild geometry, f is equal to b and is equal to 1 minus 2m over r. But for the sake of generality, I will keep them generic, having in mind that, as we said yesterday, in modified theories of gravity, the Schwarzschild metric might not be a solution of the theory, it might have different solutions. And any solution in spherical symmetry will have this form. Then the proper thing to do in order to understand how this metric vibrates would be to make perturbations, metric perturbations on the top of this geometry. So taking the metric to be, say, the background, we call it G to 0 order, plus some corrections, where this is the background metric described by this geometry here. So it's a static geometry. And then I want to understand the perturbation, the dynamics of this perturbation here. Of course, in order to do that, I need a theory, because I need to plug this decomposition into the field equation of my theory and compute at linear level the dynamics of the perturbation entity. So this procedure can be done, is done on a theory by theory basis, but yeah, of course, it's model dependent. In order to just make you understand the idea, I would instead take, instead of doing magic perturbation, I will take a test scalar field. Just because the key ingredients that I want to discuss are the same. And so what I want to do is take a simple plain Gordon equation, box phi equal to 0, and I want to study this equation on this background. So I will neglect the back reaction of this scalar field onto the geometry. I just want to study how this propagates in this curved geometry. And this is much simpler because I don't need to specify any theory. It will only depend on the background geometry. Of course, say the model for my theory is described by the Tortoise Coordinate. So it's simple to use the fact that this metric is spherical symmetric and stationary, and use this fact to decompose this field that generically depends on all space-time coordinates in a suitable basis for spherical harmonics. Call it psi of spherical harmonics y ln theta phi, and enabling a time dependence given by the e to the minus I omega. Okay. So the possibility of making this spherical harmonic decomposition, and the fact that it's very useful here, is because the metric is spherical symmetric. It would not be true otherwise. And because it's static, I mean, there is a frequency that is conserved, and this is why one can do this decomposition. So it's easy to see that if one plugs this decomposition into the Clay-Gordon equation and use this background metric, the field equation for this radial function here, which is the only unknown of the problem, is the following. Remember it. So it's the following form: f d sine second 2 plus 1 f prime d prime f psi prime plus omega squared minus d psi 0, where b, let me write it here, b of r is f L plus 1 divided by r squared b prime to r plus b f prime divided by 2r. Okay. So it's a simple exercise to really write the Clay-Gordon equation with the composition, and because of spherical symmetry, each of these modes, actually this mode depends on L, so this is an L here, an L here, and an L here. They decouple from each other, and one gets a single differential equation for these perturbations. Okay? So in this form, seems complicated, but in fact, if one does the following changes of variables, one can define a variable x such that dr dx is equal to square root of n times p, if I'm not mistaken. So by doing this change of variable, the final result is very simple. Is this one, d psi l dx squared plus omega squared minus b psi equal to 0. So one finds this equation that is essentially the time-independent Schrödinger equation for a given potential that depends on the metric coefficients in this form. And this is true for any metric, spherical symmetric metric that one can think of. And in fact, it is true even in GR for gravitational perturbations, It is possible to decompose them in axial and polar modes. Probably you have seen this during the Poisson lectures. And there is what is called a master equation that describes the axial and polar sector, and it has precisely this form for some given potential that depends on the geometry. So in this coordinate x is typically called Tortoise coordinate, and it has the properties that it goes to r when r goes to infinity, and it goes to minus infinity when r goes to the horizon of the geometry. So it's defined in this way. In this coordinate, the potential typically, at least in GR, but this is true in many theories, has this shape. So this is V, this is X. So here is plus infinity, and here is the horizon. And of course, it's called Tortoise coordinate, well, for two reasons. First, because the horizon is at infinite distance in this coordinate, and also because the relation, at least in the partial geometry, between x and r involves a logarithmic term. So x goes to minus infinity logarithmically. So it's a slow dependence. Okay, but so the important point is that this potential is a maximum, which roughly corresponds to the photosphere of the geometry in GR, and it defines a scattering problem the same way one would have a scattering problem in quantum mechanics for a time-independent Schrödinger equation. So this is a linear equation that depends on the frequency omega, and if we set boundary conditions at both boundaries, it defines an eigenvalue problem. And in particular, for these boundary conditions, so having purely outgoing waves at infinity, so waves which behave as e to the I omega x, so that they move to the right, and waves which are purely going at the horizon, so they behave as e to the minus I omega x. With these boundary conditions and these equations, this is an eigenvalue problem that defines an eigenspectrum. So say this equation plus the boundary conditions defines the so-called quasi-normal modes of the system. So the frequency, the eigenfrequencies of this problem, which are complex, in fact, and can be written as a real part and an imaginary part. The real part is associated with the oscillations of this mode, so this is the mode frequency, and the imaginary part is the inverse of the damping time. So it tells us the time scale over which this perturbation is damped, and the reason why it's damped is twofold. Is because these boundary conditions are dissipative, both at infinity through emission of the gravitational waves, but also at the horizon, because the horizon absorbs radiation. These quasi-normal modes in general should be computed numerically, except for very specific choices of the potential. But in GR, they are computed numerically, and they typically depend on the number L, so the angular momentum quantum number. They also depend on the number M that define the azimuthal number in the spherical harmonic decomposition. And for each L and M, they also depend on an index N, which is called Overton number, and essentially is just a label that counts the infinite set of modes that exist for a black hole in essentially any theory of gravity. So for a fixed say mass of the Schwarzschild black hole, there is an infinite set of quasi-normal modes defined by L, M, and N, and the dominant one is clearly the quadrupolar, L equal 2. For a Schwarzschild black hole, N is not relevant, let's say, let's take it's 2 N equal 2, and the fundamental mode is the one labeled by n. There is a fundamental mode with a given frequency and damping times that dominates the signal. By dominating the signal means, I mean that, let me keep this for a moment. By dominating the signal, what I mean is that a complex frequency of this form has a oscillating pattern of this form here, with a minus, and then there is e to the minus t omega I. So the bigger omega I, so this oscillating, this is actually damped whenever omega I is negative, or exponentially growing if omega I is positive. But in that case, the perturbation would be unstable. So for stable perturbation, in this, I mean, my notation, omega I should be negative. And the bigger omega I, the smaller the time scale, so that the damping time tau is equal to 1 over omega I, absolute value. So the bigger omega I, the smaller the damping time, so the smaller the time scale for this perturbation to die off. And therefore, the dominant mode is the one with the biggest imaginary part, sorry, with the smallest imaginary part, because it's the one with the longest time scale. So to clarify this point, the signal here, if one writes the waveform, so this psi is a function of time, it would be something like this. So there is an envelope that depends on e to the minus t divided by tau, and then an oscillating pattern, so it's modulated by this envelope, and therefore how fast the signal dies off depends on tau, and of course the oscillation depends on omega. Okay, so I mean this was a primer for quasar modes in GR, even though we didn't linearize an equation, but as I was mentioning, everything I said applies also to gravitational perturbations. It's just more complicated. But the crucial point to understand is the following: that these quasi-normal modes that we can compute numerically by solving the eigenvalue problem depends on three quantities. I mean, on three aspects. So the first aspect is the background geometry, because this potential depends on the background geometry. So if I change the geometry, I will also change the quasi-normal spectrum. The reason is simple, that a slightly different background geometry will have maybe a potential that is similar but not exactly equal to the one of a sparse black hole, for example. And so this will modify the spectrum. The second point is that it depends on the dynamics of the theory. Here, I was just discussing a test scalar field described by the Klein-Gordon equation, but you should think about it as a proxy for a gravitational theory. So if I change my theory, even if the background geometry is the same, the potential will be different, because in order to find the potential, we have to linearize the theory under a given background. And even if the background is the same, the way the perturbations propagate might be different. And there are examples of this. Yesterday I mentioned what is called dynamical Chern-Simons gravity. It's a specific quadratic theory of gravity. In that theory, the Schwarzschild solution is still a solution. So the static solutions are the same as in GR. Actually, spherical solutions are the same as in GR. But if one computes the perturbations, one finds that the master equation, the one describing the quasi-normal modes, is different. It's actually a system of two coupled Schrödinger-like equations with different potentials. So even if the background geometry is the same, the theory modifies the potential, and therefore the quasi-normal spectrum is different. And finally, The third key ingredients are the boundary conditions. And the reason is that, of course, this is an eigenvalue problem. So the Quasar modes depend on the boundary conditions that we are imposing. Now, imposing purely outgoing waves at infinity is natural if we want to study the proper oscillation frequencies of the system. I mean, we don't want waves to come from infinity because they would interact the system in a sort of source wave, right? In a sort of stimulated wave, and we don't want that. But a crucial ingredient is this one here. And the reason is that for a classical horizon, we expect all the radiation to be absorbed. I mean, by definition, there can be no any radiation emitted in this direction, because if there is a radiation emitted in this direction, this will not be a black hole, a classical black hole by definition, because it's a perfect absorber, right? So it's interesting that even if the background geometry, say, let's suppose that is that is exactly the same in the exterior. I mean, from some point on to the right of this diagram. Even if the theory is described just like general relativity, if for some reason the boundary conditions in the deep interior of our object, so very close to the event horizon, are different for whatever reason, then we would have to change these boundary conditions, and this would have drastic changes to the quasi-normal spectrum. So these three ingredients all contribute and conspire to give us a specific quasi-normal spectrum, and this is why testing the ring down, so this is the ring down signal. This is why testing the ring down signal is so important, because there are different ways orthogonal to each other that would modify this frequency. So if we are able to measure these frequencies, we would have a great way to test the theory. And also the nice thing is that this is linear perturbation theory, so it's relatively simple and also clean, as much cleaner than other probes which would require nonlinearity. The price to pay, of course, is making sure, and this is highly non-trivial, that the data that we use, so the signals that we use, are in fact well within the linearized regime, so for perturbation theory to apply. This is an important point because the full coalescent signal, so let me just draw it as an illustration. We will have something like this. So I'm spiral with the shear, the amplitude and frequencies are growing, and there is a merger, and then the signal dies off quickly, right? So let us suppose that the merger is about around here when the signal is maximum. It's clear that immediately after the merger, there is no reason to expect the remnant to be a stationary configuration plus small perturbations. Most likely is highly deformed, highly dynamical, so we cannot definitely start the ring down analysis from the peak of the merger, the peak of the waveform. But we want to wait a certain amount of time and start, for example, the ring down analysis here, where the signal is already smaller, and we might expect the final object already to be almost settled down to a black hole. This is fine, but there is a price to pay, that the signal from now, I mean, after the merger, dies off exponentially, which means that if we wait long enough, we are sure to be in the linearized regime. But if we wait too long, the signal is exponentially suppressed. So effectively, the signal to noise ratio contained in that portion of the signal is negligible, or anyway small. So the quality of the test that we can do is also reduced. So an important problem that we say is an problem is how to find, to strike the best balance between starting as soon as possible the ring analysis without compromising the linear nature of the theory. And recently, an important point that has been made is that including overtones is actually might actually be relevant, in the sense that if one, instead of considering a single mode, starts including also the overtones for a given L and M mode, then it is possible to match the signal better than by considering only a single fundamental mode. But this is something that is still debated and actually under investigation. Okay, so a few other comments I want to make is that I was focusing on the static case, so no spin. What happens in the spinning case? So luckily enough, for a Kerr black hole, the linearized perturbations are still separable in terms of what is called the Tortoise equation. And the final result is that we have very accurately, with actually infinite accuracy numerically, the quasi-normal spectrum of a Kerr black hole, and it depends, as it must be, on the mass and spin of the object. I recall that m is the mass, phi is j over m squared, and for a Kerr black hole is between 0 and 1. Okay? This is also great because it means that the entire quasi-normal spectrum, so these numbers, n, l, and n, so L runs from 2, 3, 4 to infinity, n goes between minus L and L, but it's an integer, and n goes to 0, 1, 2 to infinity. So there is an infinite set of quasi-normal modes. Of course, some are more important than others because only those that live longer will be detectable. Those that live very shortly will just die off much more quickly. But the entire quasi-normal spectrum for a Kerr black hole depends only on two parameters, mass and spin. What does this mean? It means that if we detect one quasi-normal mode, meaning a complex frequency, so frequency and damping time, then we can invert this relation to find the mass and spin of the random. If we detect two quasi-normal modes, or at least three quasi-normal mode quantities, for example, two frequencies, the frequency of two modes and one damping time, for example, or four quantities, two frequencies, two damping times, or the frequencies of three modes and some damping times, I mean, any possible combination. If we detect more than two quantities, then we can test really the theory, because the first two measurements will be used to set the mass and the spin. From the third measurement on, we can check, so we can do an analysis test of the Kerr geometry and understand whether the full spectrum is compatible with what predicted by a Kerr geometry. So in particular, we can detect one mode and check for that given mass and spin in third mode if another mode, a secondary mode, is compatible with the Kerr hypothesis or not. A more concrete way to do that is to, let me clear, is to again deform the spectrum in a way similar to the parametrized approach that we discussed yesterday, in the following way. So we can have a real part that for say n, and n can be written as the real part for Kerr plus some correction omega r that is the final. And same for the imaginary part. And therefore the point is trying to put a constraint on this correction. So on these deformations here, these deformations are 0 for Kerr, but they for care in GR, this is important, but they might not be zero in modified theories of gravity, or if the object is not care, or anyway, if there is any deviation from general relativity. There is a problem compared to what I said yesterday, because yesterday I said that the parameterized, for example, the PP parameters are just numbers that potentially, I mean, given a theory, they would depend in some analytical form, because the equations can be solved analytically, in terms of the binary masses and spins, and extra parameters such as coupling beyond GR. Here is more complicated because the spectrum of Weissenberg modes is not only numerically, even in GR, so we have to solve some numerical equations, which in modified theory of gravity can be particularly complicated, because maybe the equation is not separable, maybe the background geometry is not even known analytically. This can also happen. But in general, these corrections here are some unknown functions of the mass, the spin, and say beyond GR effect, which means typically couplings of the theory. And this is a problem because it essentially means that for a given theory we have to compute the Poisson spectrum for all spins and also for all couplings potentially. So it's very complicated. There are frameworks, more or less sophisticated, depending on which framework one studies, that tries to parameterize these corrections in a given way. In particular, there is a framework is called PARSPEC, and it was introduced, I think, in a paper. I think in 2019, if I'm not wrong, and the idea is to parameterize these corrections, either real and imaginary part, by doing a spin expansion. By doing a spin expansion that is valid in principle only to small spins, but extending this to very high order, in order to isolate the beyond GR corrections in a way that would depend not only, I mean, not anymore on the spin, but only on the coupling constant of the theory. So I don't want to enter in details, but there is a way, at least this perturbative expansion of the spin, to sort of disentangle this dependence on M, chi, and beyond GR effect, and come up with a parameterization that really depends only on numbers. And this is important because you want something which is simple, but yet flexible to both constrain the parameters and having a one-to-one mapping to a modified theory. The price to pay, as you can see here, from here is an index n. Actually, not n is misleading because we call it p, because n will be overall number. The price to pay is that there is a proliferation of the number of parameters for a parameterized bring down waveform that makes things very complicated to deal with. And most likely it means that one needs many events, many read down events to put constraints on this parameterization. So let me now mention what we know so far from the read down. So for the events that for which the read down has been effectively detected, probably the prototypical event is the first one because it was quite loud and also it was quite loud and quite heavy, so the ring down was clearly visible and detectable. The problem is that, I mean, in a few words, for none of the events detected so far, as of today, there is a clear evidence for a secondary mode. So the fundamental mode has been detected for several of them, including the first event. But as I was saying, detecting one mode does not allow for a proper spectroscopy test of the Kerr metric, because a single mode allows only to measure the mass and the spin of the ring. There are indications of secondary modes in certain events, in the first one, for example, and in the very massive one. So the two events which are more relevant in this context are 150914 and 190521. This was the first event, and this is the most massive binary detected so far. So the remnant of this guy is very massive, and the ring down was a very important part of the signal. The spiral for this event was very short, and in this event there are indications of the first overtone, even though this is still debated, and well, I would believe more studies are needed here to make sure that this measurement of the first overtone is solid. And here, for this event, there was recently such a claim for a detection of an angular mode, a different angular mode, an N equal 3 angular. But with very low SNR. So also in this case is not a very solid measurement. There is some SNR for the second event, but is anyway small. So the state of art is that for none of the event, two poisson modes has been detected with very strong evidence. But this does not mean that we cannot use the ring down to make important tests. And the reason is that one can do what is called IMR, consistency tests, which are the following. So for practical reasons, between yesterday and today, I'm discussing the spiral and the ring down separately. But in fact, the real analysis is done using templates, gravitational templates that include the spiral merging ring down in a sophisticated way that incorporate post-Newtonian theory in the early spiral, black hole perturbation theory in the ring down, phenomenological models to match the spiral and the ring down together, and then fit to simulations, mechanistic simulations, to come up with a complete and very accurate spiral merger ring down signal. So a signal that describes the entire coalescence, gravitational wave coalescence. Which means that we can try to use portion of the signal and see whether essentially the posterior distribution of parameters that we can infer from portion of the signal is consistent in if we take different portions. What I mean is that by using an spiral measuring down waveform, starting from the initial masses, the initial spins, and all the other binary parameters that the time of coalescence, the phase of coalescence, etc., that my waveform depends on, I can estimate using simulation the final mass equals ns and pi s of the random. Meaning that in GR there is a one-to-one correspondence between the parameters, the binary parameters before the merger, and those of the random after the merger. Of course, if we assume, say, that the binary is made of two black holes in GR. So if it is made of two black holes in GR, if I know the binary parameters, say with infinite precision, I know exactly the final mass and final speed. There is a one-to-one, not a one-to-one, but for sure a correspondence, a unique correspondence in this direction. Of course, I might have the same final mass and final speed for different binaries, so it does not go in this direction, but at least it goes in this direction. So what has been done, and is routinely done by the LIGO collaboration, is to infer these quantities from different portions of the spiral, say, and merger phase. Then use simulations to estimate the random properties, mass and spin, and then do the same, estimate random properties from mass and spin using the quasi-normal modes. So if one detects one quasi-normal mode, then it is possible to measure the properties of the random. And this is called consistency test, because if GR is correct, and if our assumption is all the black holes are correct, these two inferences, so mass and spin of the random measured from the quasi-normal or from the spiral, this is spiral, they should agree with each other. If they do not agree, it means that the waveform template we are using is inconsistent with the data. So in some sense, GR is inconsistent with the data. If they are in agreement, it means that everything is consistent. And it turns out that this consistency test has been roughly performed and are successful. I mean, they are performed routinely, and they are roughly successful at the level of 10%. So it's not yet a great constraint. Essentially, it means that the final mass and spins detected by the two events are compatible to each other, so the posteriors overlap, and the difference in the medians is about 10%, which is, I mean, is not trivial. It's a test that is totally not trivial, and it's great that it works. And in fact, it's testing a regime which is highly dynamical, and is the first time this was tested, and it will be improved in the in the future, either with more observations, with better quality signals, so with future detectors, for example, and of course, yeah, with the signal to noise ratio. If we detect signals which are more loud and massive, this test can be improved. But I would say that the holy grail of read-down test is really to detect a secondary mode or potentially many modes with great confidence, and make sure that using only the read-down, one can put constraints on the parameters.
Professor Pani, I have a question here regarding the IMR consistency test. So I was wondering if there could be situations where modifications due to gravity would affect the inspiral, the low frequency part, and the high frequency part in a way so that when you infer the posteriors on the parameter, they would actually overlap. They would both be deviated, but when you compare with respect to each other, they would overlap. Could that happen?
Yeah, it's an interesting question. I would say that it can happen. I don't see why there cannot be some conspiracy for this to happen. I'm not aware of any attempt to do this. I mean, one could try to do it by, and I'm sure that people in the library collaboration have tried this, by introducing ad hoc phenomenological parameter in the spiral measuring down waveforms and play with them to see if they can accommodate deviations in a sort of hidden way. But the proper way to do that, what we are suggesting, would be to have a fully spiral measuring down signal for a modified theory of gravity and check whether this can happen. So check whether if I infer the spiral parameters and they are different, and then infer the random parameters they are different, maybe this consistency test for the way they are linked to each other is still passed because of some conspiracy. The problem in doing this is that right now we don't have very accurate experimental written waveforms approximate for modified theories of gravity. And the reason is that one way or the other, at least if one wants to have the same accuracy as in general relativity for these waveforms, one needs fits to simulations. And well, simulations in modified gravity are tough, and well, they've been performed only very recently. So in the future, for sure, there will be such waveforms available, and I believe that yeah, what you are suggesting there will be something interesting to test.
Okay, thank you. And I see there is another raised hand. Could you please go ahead and ask your question? I can't actually hear you, Divya Jyoti. Are you speaking? Okay, just to check, is it just me? Yeah, now I can hear you. Yes.
Sorry, yeah, maybe something with my microphone. So I wanted to ask that in most of these tests, the templates or the assumptions that are taken are that the objects are binary black holes. So what happens when we actually do find some deviations, and how do we, how do we determine whether the deviation is because the object is not a black hole, or whether the deviation is because the theory of GR is not correct? How do we make that distinction?
Yes. So it's a great question. But the short answer is that it would be difficult, and it would be done on a case-by-case way, in the sense that it will really depend on the deviation one sees. In some sense, there are cases in which modified gravity degenerate with, say, non-black hole sources. For example, what I mentioned yesterday. Yesterday I was mentioning the quadrupole effect on the spiral that enters at 2 p.m. order, right? Let's say what happens there is that if the object is not a black hole, so take for simplicity a neutron star, the quadrupole moment is different from the Kerr value, and so it will modify the 2pm coefficient. But also modified theory of gravity typically modifies the 2pm coefficient. So just by detecting an anomalous 2pm coefficient doesn't tell us much. If we focus on that particular effect, it can be a modified quadrupole term, or it can be a modified theory of gravity. Of course, things are more complicated because for a given theory, we will have an entire tower of post-Newtonian parameters that depend, say, just on the coupling. And also for a given non-black hole model, is not only the quadrupole, it will be also the log number that is non-zero and other higher order post-Newtonian terms. So by putting all this information together, one can possibly distinguish disentangle two different scenarios. This, of course, becomes a case-by-case analysis, because I would say that detecting some anomaly is relatively simple. Maybe we will never do it, but it might be possible. Going from the anomaly to what produced that anomaly is much more complicated. It really depends on the source, because there will be sources in which we detect only the spiral, and then we don't have access to the ring down to test whether, I don't know, even the ring down is modified, or the other way around. For example, in this source here, essentially we detected only the ring down almost. We cannot use this source to detect -1 p.m. effect, because the spiral is too short, so we don't really see the early spiral. So the final result will really depend a lot on the situation. I would say that for modified gravity, it might be a bit easier, because module, the things I mentioned yesterday about the charges and things like that, if GR is modified, we should see the signatures in many different sources. And if you are starting detecting several sources, I mean, dozens, there is really no reason why there should be GR modification in one single source and not in the others. It would be very unlikely. On the other hand, if the objects are not black holes, that's more challenging because one may imagine that in the universe there are black holes, neutron stars, maybe, I don't know, boson stars, and therefore, if I detect an anomalous event, that might be a different class, a different family of compact binaries that we never detected before. So that will be more hard to rule out, and it will, I guess it will also depend. I mean, the analysis will be done case by case, model by model, to see which one is approximating better the data. Having said so, I mean, I will take this question to move what I want to discuss in the last minutes, which is a modification of the ring down that is typical. I mean, it's very peculiar, and it does not have to do with modified quasi-normal signal, but it has to do mostly with the post-merger phase and how the signal looks like, even after, let's say, the prompt ring down. And this might be something that can be used to disentangle modified gravity effects from non-black hole effects, which was the point of the question. But before going there, actually, let me just mention something else that I think it's interesting and I didn't tell you. So in GR, let me take GR as Schwarzschild. So if you probably heard from some lectures, there are two sectors of the perturbations. The gravitational perturbations are described by the axial and polar sector. They are different because they behave different under parity, and they are both described by this equation here. Where V is different in the axial case or in the polar case. They are pretty much similar. So if you plot them, they will be something like that. So very similar to each other, but not quite. So the maximum is slightly different. And yeah, I mean, the shape qualitatively is the same, but the potential are different. So there is no reason why these two potentials should have the same quasi-normal modes. In principle, they should have different spectrum. What it happens is that the quasi-normal modes are isospectral. This was a property proved some time ago by Chandrasekhar, that because of some symmetries that exist between the axial and polar sectors, so some transformations that map the polar sector into the axial sector and vice versa, the quasi-normal modes of axial and polar perturbations are isospectral for Schwarzschild black holes. This concept of axial and polar is not true anymore for a curved black hole, but still, for a curved black hole, the modes that, I mean, these two families of modes that really coincides in the Schwarzschild remains the same also for a curved black hole. So, roughly speaking, there might be two families of modes in even for a given L, and M, okay, which are related with different parity perturbations in GR, but it doesn't happen. This doesn't happen. So for this spatial symmetry, we just have one family for each L, N, and M, and this is called isospectrality. These isospectrality broken essentially in any other case. So if you have non-black holes, or you have modified gravity, or the background is not Schwarzschild, something else, this is broken. And by broken means that we should expect that for each N, L, and M, instead of having a single mode, we should find what is called a mode double. So two modes that are very close to each other because they have to be the same, overlap each other in the GR limit, but in beyond GR, they form a doublet was, say, frequency distance possibly is related with the beyond GR effect. So most likely, say, delta omega mod 1 minus omega mod 2 will be proportional to the coupling constant of the field. And therefore, in the GR limit, this difference is zero. So this is another sort of model-independent feature that one may look for, is seeing whether there are mode doublets in the data. It's very challenging because frequencies which are very close to each other needs to be resolved, so resolved apart, and this might be challenging. Actually, it's probably more challenging than the test that I was mentioning before, but yeah, it's something that people can look at to find at least model-independent ways to test the ring-down properties of GR. Okay, so this was, yes, something else I want to mention. Let me close with something else, which I find particularly interesting related with the ring-down. And to do that, let me start again with the effective potential. And I was mentioning the quasi-normal modes are the modes that are defined by the eigenvalue problem with these boundary conditions. Purely ongoing at infinity, purely involved factorized. Now, this boundary condition here, as I was mentioning, is really essentially is by is imposed by the very definition of a classical black hole. And classical here is important because we know that classically black holes absorb every radiation of any frequency. But this might not be true if the properties of the horizons are not totally classical. For example, if they have some quantum properties, we would expect not all radiation to be absorbed, maybe some is reflected. Or if the object is not a black hole, so it does not have a horizon, part of the radiation would be reflected. For example, for a neutron star, actually the same amount, so if this radiation is an amplitude A that goes on the left, for a neutron star, the same radiation is actually reflected because the neutron star does not absorb any gravitational wave. The interaction between the neutron star matter and gravitational waves is totally negligible. So effectively, neutron stars are transparent gravitational waves, which in this one-dimensional picture means that all the radiation that goes in eventually goes out. Okay? Which can be can be modeled in a way, in a more mathematical way, saying that the reflectivity of the neutron, the object in this case, that I would call R squared, is equal to 1 for a neutron star, while the reflectivity is equal to 0 for a black hole. So this property that the object reflectivity is 0 is really can be taken as a sort of broad definition of how a black hole behaves and the boundary conditions that should be imposed on the black hole horizon. For a neutron star, instead of being 0, is actually 1, so there is a total reflectivity, and we expect reflectivity to be 1 for any object that does not absorb gravitational waves. For black holes in modified theory of gravity, they are classical black holes, they will have 0 reflectivity. If there is some quantum property, for example, part of the radiation is reflected back, we might have some reflectivity, which might be small, might be frequency dependent, and so on and so forth. So an interesting point is, can we constrain the reflectivity of the remnant object that is formed after the merger? And in order to do that, what one can do is to model this problem by having the same potential as for a partial black hole, and then introduce an effective surface. So this is say at position minus x naught, and the effective surface takes radiation that goes on the left and then adds a term that is a reflective wave that goes on the right. So there is part of the radiation that goes on the left, part of the radiation that goes on the right. And for a given model of this non-classical black hole remnant, one can prescribe a reflectivity, which is generically frequency dependent. And well, what this will do is modify the boundary conditions of your problem, and therefore the Quasimodo spectrum. So for any R, you will have different Quasimodo. Now, an interesting point, this is why I was saying this is very different from a standard modifier down picture, is that let us take even the most extreme case. So the reflectivity is unity, so everything is reflected. What would happen is that the quasi-normal mode spectrum of an object with perfect reflectivity and whose surface is very on the left of this diagram, so very close to where the horizon would be, is totally different. So the quasi-normal spectrum does not even reassemble the one of a black hole, and the reason is that a partially reflective surface here will create bound states between this maximum, which is, as I was saying, roughly the photon sphere of the space-time, and the object interior. So if I take for a neutron star, actually this does not really happen because the neutron star is not that compact to have a photon sphere. But if you had a photon sphere and it was perfectly reflective, we would get something similar like this. And in fact, this kind of modes for stars have been studied again by Chandrasekhar and Ferrari in the 90s, in the 1990s. And what they found are the so-called S modes, which are just trap modes between the potential barrier and the object interior that only exist if there is some reflectivity. If there is no reflectivity, these modes do not exist because they will just be absorbed by the photon. What happens is that these trap modes, if I call these, let me see. Okay, if I call this X naught, the real part of this mode, if I'm not wrong, goes like 1 over X naught, and the imaginary part goes like, well, this might be wrong, but it doesn't matter really the power, some power of omega. Okay, and the reason for the existence of the spatial mode is clear, is that because there are bound states, the frequency is given by the width of this cavity. That is, so I'm taking this to be the origin. So it's roughly scaling like 1 over X naught. So the bigger the cavity, which means the more compact the object is, the smaller the frequency. And same here, the smaller the imaginary part. So tau, the damping time, grows as X naught to some power, positive power. I think it's either 12 plus 1 or 12 plus 2. I don't remember. Which means that if I put this effective surface very on the left, the damping time of this mode is huge, and these modes are those that dominate the signal in principle. So that at very late times, they would be the ones that survive the most. Now, the curious thing is that if you take one of these models and you compute the ring down, what you would get initially is something like that. You will get actually the very same ring down of a Schwarzschild black hole. Almost exactly, actually it becomes exact in the limit in which X naught goes to infinity. So it goes to here on the left. Okay? And the reason is actually pretty clear, is that the scattering problem of your defined by your potential does not care about the boundary conditions imposed on the surface, as long as the radiation takes sufficient time before reaching the boundaries and eventually coming back there. So this is something not totally well understood, not totally well recognized for black holes, that the boundary condition I was mentioning before, the purely ingoing boundary condition at the horizon, is reached in infinite time. So effectively, the Poisson spectrum of a black hole really depends only on the local properties of this maximum and not on the boundary conditions there. And this is why, if we change the boundary conditions, but only when we are very far away from this potential, so when there is this cavity, the prompt ring down, what I would call prompt ring down, is equivalent from that of a Schwarzschild black hole, and is actually universal. It does not depend on the boundary conditions at all. What happens is that later on, after the radiation has taken sufficient time to reach this boundary and then goes back, so in a time that is roughly 2x naught, what happens is that part of the radiation will be re-emitted, will tunnel this potential and leave the system, being emitted in gravitational waves. And it can be proved that the secondary radiation is a sort of reprocessed ring-down signal. So it's a signal that is found by reprocessing through this potential barrier and dynamics the prompt ring-down. And this goes on and on, because this radiation is partly reflected by the potential, partly reflected back, is then reflected again through this potential, each time being reprocessed a little bit. So what happens is that the amplitude decays, the frequency content also decays, but a crucial ingredient is that roughly each of these echoes, so these are echoes of the prompt ring-down signal, are repeated on a time scale 2x naught. And and this is really a smoking gun signature of something that is not a modified Poisson spectrum. Here the spectrum is modified, but in fact, if we just look at this portion of the signal, it will be exactly the same as a black hole. But by looking at these bursts later on, after a certain amount of low frequencies, low amplitude, and they are repeated, we might look for this effect. And in fact, the distance between echoes, so the echo delay time depends on x naught, the amplitude, so how much the amplitude is reduced, depends on the reflectivity. So by putting constraints on this effect, we also put constraints on the effective reflectivity of the remnant. Interesting enough, since probably the second gravitational catalog, the library of collaboration is looking also for this effect through many different waveform parameters, waveform templates. Finding a proper parameterization and templates for this signal is actually very challenging. There are several hypotheses and several models, but yeah, the net result is that there was no detected signal so far. So this has been used to put constraints on the reflectivity of the audio and also this parameter x naught. And this is essentially another orthogonal way to look for modified gravity or modified black hole features in the ring down paper. Okay, so I think I'm running out of time, so I will stop here and I'm happy to take questions.
Thank you very much, Professor Pani. And I see that there is a hand raised, so I'm just going to allow the person to unmute. Please go ahead and ask your question.
Yeah, thank you very much for the lecture. I have a question actually about MRAs. So what about perturbation theory that we use in the emergent spiral and also in the remnant? Can we also detect in the remnant that we had the case of MRA? And what's the difference between the two formalisms that we use in the spiral and in the ring down for MRAs?
Okay, apologize. I could not understand the question. The audio is not great. I don't know if someone can repeat it, please.
So I can try to repeat the question. I think roughly it's whether the formalism that you use for black hole ring down here, would that also be applied to the MRIs, extreme mass ratio in spirals?
Okay, so for the ring, okay, so for MRIs, the ring down is not really relevant in the sense that the point particle will eventually plunge into the big object, the supermassive object. There will be a ring down, but the signal to noise ratio is really small because it will be really a tiny perturbation. I guess the question was, however, whether black hole perturbation theory can be used to model MRIs. In fact, it can, in the sense that beside computing the quasi-normal modes, a potential of this form and an equation like the one I was mentioning before can be used to compute energy fluxes. So how much energy is emitted, say, by a point particle orbiting around the supermassive object. And the idea is that the quasi-normal modes are the free oscillations, so there is no source, but if there is a point particle in the space-time of the object, it will follow a geodesic motion, which will adiabatically change through gravitational emission. That can be computed with essentially the Minkowski equation. This is to zero order, so it's really the leading order effect that one used to model MRIs. Then there is an entire very sophisticated technique related with self-force and how to incorporate finite size effect in these dynamics that essentially goes order by order in the mass ratio of the binary, and trying to incorporate also the back reaction of this radiation onto the geometry and so on and so forth. There are a lot of progress recently in the community, and people are starting computing second order self-force effects, which will be important for LISA. It's all based on black hole perturbation theory and the back reaction of this perturbation geometry. So yeah, I mean, a much more sophisticated formalism than one I was mentioning now applies also to MRIs. The very generic idea though is the same. So perturbing a black hole with some source.
Yeah, just for MRIs, can we use some parameterization to have constraints on the hair for hair black holes using MRIs? Because in case we have different quasi-normal modes, it's signal smoking gun of having a new charge. So what about trying to detect this hair on the end, for example?
Yeah, I apologize. I also have to ask someone to repeat the question because my speaker is really bad.
Again, I can give it a shot. I think what the question is asking is whether in the case of MRIs, one can put constraints on extra hairs of the black hole.
Okay, so yeah, this is a good question. So the simplest answer is extra hair of the supermassive. Well, let me try to make a comprehensive answer. We can distinguish between the hair of the supermassive object and the hair of the secondary object, the small guy. For the hair of the supermassive object, because of the hair, one would expect the geometry not there. It would be a different geometry with some different profile, and for example, different multiple moments. But even regardless of the multiple moments, the geodesic motion will be different. So even if I neglect the fact that maybe these hair are due to a modified theory that also modifies the dynamics, also modifies the gravitation wave emission, even if I neglect that, considering the same gravitation wave emission of GR in this modified geometry would allow to put constraints. And the reason is that the MRI will make a lot of cycles around the supermassive object, probing the geometry. So there will be a phase difference and an amplitude difference due to the fact that the big guy has some different profile, different geometry, different space-time geometry around it. If the small object has hair, the situation is somehow simpler, and it's actually very relevant because there are theories of gravity, like the quadratic gravity theories I was mentioning before, that are relevant only at high curvature, and the small object has a much higher curvature than a supermassive one. So in this theory, the supermassive object is described by the Kerr metric, so the geodesics are the same as Kerr, but the secondary object might have, for example, scalar charges, like those that I was mentioning yesterday. So in this case, the situation is reversed. We have the same conservative dynamics, the same geodesics, but different gravitational wave emission, for example, because there is extra scalar air in the secondary, and therefore fluxes are different, and essentially the orbit shrinks in a more or less time, depending on the theory. So those are two orthogonal ways to look into hair in MRIs. The reality, though, is that given a theory, we would expect both different geodesics in the supermassive object and different gravitational wave emission. So the two things, again, like I was mentioning yesterday, conspire to give a different signal. And so we will probe hair in this more complicated setup, most likely.
Okay, since I see the participant doesn't have an additional question, I will again ask the rest of the participants or even the panelists, does anyone have any other questions? Okay, if not, I actually do have one question. This is regarding the echoes topic. I guess it's sort of a general question. I'm just wondering whether there is any physical motivation to expect to have surfaces with partial reflectivity. I mean, do we have states of matter that can produce a reflectivity between 0 and 1?
Yeah, so this is a good question too. It has to be very, very weird matter in the sense that we do expect gravitational waves on generic ground to interact very poorly with. Well, actually, sorry. Let me put it another way. If there is an horizon, so if the object is a black hole, we would expect the reflectivity to be either 0 or very close to 0 if there are some corrections that we do not take into account. On the other hand, as I was mentioning, if there is no horizon, the situation is expected to be much more like a neutron star, and a neutron star does not absorb any radiation. So, effectively, any sort of ordinary matter that does not have, say, viscosity, I mean, a huge amount of viscosity, should have reflectivity essentially unity. This has actually been computed for neutron stars, and it turns out the reflectivity neutron stars is unity within, say, 1 part in 10 to 30, something like that. So it's really an excellent approximation to assume that ordinary objects have a perfect reflectivity. In order to see this effect, though, there is an important caveat that you want the object to be compact enough to have a photon sphere. And the big limitation is that there are very few models, inconsistent models coming from a theory, a Lagrangian, etc., that are made of ordinary matter, satisfying energy conditions, non-superluminous speed, etc., and having a light ring. So, I mean, by far the main objects we know with a light rings are all black holes for which reflectivity is zero. So yeah, the answer is we do expect reflectivity for ordinary objects to be actually not even close to 0, but I think more close to 1. The problem is, do we expect realistic object to be so compact? It has to have S modes or trap modes, and therefore echoes. That's more challenging.
I see. Thank you. So once again, let me just check if there are any other questions. Okay, I'm going to take that as a no. So I would like to personally and also on behalf of the panelists and the organizers and the attendees, thank you very much for an excellent set of lectures. At least for me, I found it a very illuminating overview of the subject. So thank you very much.